but also kind of very slick and practical. Now, there was one topic that I didn't quite have time to cover, so I wanted to touch on briefly, which is this question of approximation algorithm for 3-SAT. It'll be a nice example of linearity of expectation. Okay, so as you guys know well, 3-SAT, giving a SAT, 3 variables in every clause. And we know that it's, of course, NP-hard to satisfy all the clauses. It's the NP-hard problem. Another way to put this is that, if you want to look at it from an optimization perspective, and you said, I just want to satisfy as many clauses as possible, that also is NP-hard, since if you can satisfy as many clauses as possible, you can then figure out whether or not the whole formula is satisfiable. But then there's a question of, is it hard necessarily to satisfy 50% of the optimum solution? Right? So at some level, it's not necessarily NP-hard to satisfy, say, half the clauses, because it doesn't really tell you whether or not all the clauses are satisfied. Right? So it's sort of a different question. On the other hand, it's still a very practical question to be given a lot of constraints and just try to satisfy as many as possible. You can imagine that showing up in a diverse set of contexts. Okay. So I thought I would open up the floor. If anyone wants to take a guess, I know some people already know this, but a shot in the dark at a reasonable strategy to, say, try to satisfy half the clauses in a 3-SAT formula. Yeah, sure.
Just randomly guess between true or false for each
Okay.
clause.
Yeah, so I know that I've discussed this with some of you before. So a very silly approximation algorithm, one that really doesn't even look at the SAT formula and its structure, is to just assign every variable true or false independently at random. Okay, so for each xi, I'll flip a fair coin, true or false, comes up heads or comes up false. Okay, and that would be my satisfying assignment. All right, that seems like a very silly algorithm. It is a silly algorithm. But let's look at how it performs. So let's look at a particular clause, right? Here, x1 or x2 or not x3. If I flip coins for all 3 of those variables, I'm hoping to satisfy the clause. So I'm going to satisfy this clause unless x1 and x2 and x3 are particular values, which I've left blank. So in this particular case, x1 or x2 are not x3. I will satisfy x1 unless I will satisfy the clause unless x1 is equal to false, and x2 is equal to false, and x3 is equal to true, right? So basically you flip 3 coins, and there's only one outcome of all 3 coins simultaneously that won't satisfy the clause. Okay? So they are independent coins. This will show up as probability 1/2. This will show up as probability 1/2. This will show up as probability 1/2. Right? So you only have a 1 in 8 chance of screwing up that clause. Okay? So, alright, so you have a 1/8 chance of failing a particular clause. That means the probability that this clause is satisfied is 1 minus 7/8, or sorry, 1 minus 1/8, which is 7/8. Okay, so any particular clause is going to be satisfied with probability 7/8 because you have to be pretty unlucky to not get that clause. Okay, you flip 3 coins and they all go the wrong way. But we're interested in trying to argue that I satisfy all the clauses, a fair amount of all the clauses, and I've only analyzed one. Okay. So now my question to you is, what tool might I use to try to figure out what's the average number of clauses this algorithm will satisfy? Yeah.
Can we try to find the expected value?
Yeah, so we want the expected value. And we're going to do a setup that's similar to, I forgot to erase it, that's okay. We're going to do a setup that's very similar to quick sort, where I introduce a variable xi, that's 1 point if I satisfy the ith clause, and 0 points if we don't satisfy the ith clause. Okay. So, the expected number of clauses satisfied is the expected sum of these xi's, right? The sum itself may be complicated, right, in the sense that these clauses aren't disjoint and independent from each other. Maybe if you satisfy one clause, it's impossible to satisfy another clause. That could happen. That could not. Okay. But since we're only looking for averages, here we can apply linearity of expectation. Right? Linearity of averages. And then I get the sum of averages. And every clause will give me 7/8 of a point on average. Okay, so for 3-sat, if you just assign true or false to everything, you'll get on average 7/8 of the clauses. Okay, so that's a simple algorithm. 7/8, is that good? Is that bad? Certainly the algorithm isn't very clever. Okay, so here's a remarkable. Okay, that's what it was. Here then is a remarkable fact that I only mention. It's very hard to prove this thing. But maybe it's one of the more impressive things we've proved before. This is called the PCP theorem. PCP stands for probabilistically checkable proofs. So we showed that sort of the silliest algorithm in the world will give you 7/8. But if you could do a better algorithm, if you got an algorithm that can get 8/9 of the clauses, okay, if you could get 8/9 of the clauses, then actually that's equivalent to just solving the SAT altogether. Okay, so any approximation factor that's strictly better than 7/8 by some fixed constant factor, 7/8 plus 0.000001, that's also NP hard. Okay, so amazingly, this might be the best algorithm we can do, at least from a worst case analysis point of view, for 3-sat. Yeah.
Is there a problem? So I know there's not an independence problem for the linearity of the expectation, but is there a linearity, or is there an independence problem sort of inside that expectation? And if you have multiple variables that are like mutually exclusive, kind of?
Yeah, so actually that's sort of the beauty of linear expectation here. So I think with SAT, it's very easy to see that two clauses are not at all unrelated. You can have x1 here and not x1 in the next one, right? And in general, SAT is a complicated thing. Trying to map out how all the clauses are related to each other seems to hide arbitrarily large complexity because we can't deal with SAT. But linear expectation kind of cuts through all these dependencies like a knife through butter. So there's something. So this is exactly why linear expectation is so useful, is that it lets us look past some of the inherent complexities of a random process. All right, so that's what we didn't cover last time. But anyway, so it's just interesting. Highly consequential that we also can't do better than 7/8. In general, the general idea of approximations having limitations as well is a deep idea. Okay, so on to today's planned topic. All right, so today is going to be our first lecture using hash functions. Okay, I'm sure you guys all use hash functions all the time, whether or not You realize it. And we're going to look at this very interesting problem called heavy hitters problem. As our first example of hash functions, and in our next hash functions lecture will be really about hash tables and implementing dictionaries. Okay, but actually that will require a little more sophistication on the probability side, so we'll do heavy hitters first. All right, so maybe you guys have seen this site before. This is Google Trends, trends.google.com, and or you've seen trending topics on Twitter or something. And so what they do is they try to keep track of, what are the most popular trends, and especially recently and stuff like that. So when I looked this morning, the following topics were trending. I actually don't know what they all mean. Maundy Thursday was trending. I'm not sure if that's what that is, but maybe you guys can explain. Neptune missile is trending. That doesn't sound good. I don't know what it is. The Hornets won last night. The Pelicans won last night. Something happened in soccer, so Manchester City is trending. Liverpool's also trending, so maybe somebody lost, somebody won. The Dodgers are trending. Some guy named Patrick Leola is trending. Somehow Cuba Gooding Jr. is back in the news. I thought he retired a long time ago. And then finally, somebody named Sherry Papini also is trending. Okay, whatever. So they keep track of all these trending topics and stuff, and I guess I could have clicked more trending searches and found more stuff. Okay. All right, so that's kind of fun and curious. Why do they do this besides just for curiosity? So they do want to keep track of what are the trending and most frequent queries so that they can save the answers ahead of time, right? Why are all these things on the internet fast? It's because whatever you think was your unique personal query, someone else did 5 minutes before you. Okay, so they save the answer. Okay. And so to try to anticipate, the most popular queries, which make up the vast majority of the queries, they need to somehow count and keep track of what's more popular than others. Okay, so so they at some level want to count and especially maintain counters for the most popular queries. Okay, but the problem they face is sort of interesting because you can query so many things to a search engine or to whatever other service, right? You can type in anything you want. A lot of it is not worth keeping track of, but you don't really know that a priori. Okay, so at some level, sort of the possible set of queries is just way too many to actually reserve a counter for each one. You want to maintain a counter for all the important queries, right? So you can know which are the important queries and maybe know which ones are more important than others, more popular than others. But you don't know which ones are the important ones. You don't know which ones to maintain a counter for. Okay, so you see this kind of thing. Okay, so that we'll call the heavy hitters problem. Okay, so we're going to reduce, kind of make it a cleaned up model for sake of discussion. So this is going to be a streaming model. It's probably the first time we've sort of moved outside a standard model of computation. Okay, so in the streaming model, elements will appear one by one online. Okay, so imagine you're a computer and you're just taking in data coming in through the internet. So here, I guess I have a list that goes A, B, C, B, A, D, A, stuff like that, right? And as the stream comes in, you can see that A is a little bit more popular than the others. Okay, and so maybe given this stream, I might ask, I want to find the subset of elements that appear at least 5% of the time in the stream, say. Okay, 5% is arbitrary. In general, we're going to just make 5% some parameter epsilon and say, okay, I want everything that appears at least an epsilon fraction of the time. Okay, and what makes this interesting is you want to think of the length of the stream as just arbitrarily long and never ending. Okay, and meanwhile you are just a small, modest computer taking in one piece of information at a time, your memory is finite, independent of the size of the stream. So this is not a situation where you can just put all the data into a text file and go over the text file again and again. You have a limited amount of space compared to the total amount of data you're trying to take in. Okay, so this is the classic general setup in some of these quote-unquote big data situations, these sketching and streaming situations. The only example we'll see in this class, but it's a common model these days. Okay. Does the model make sense? General problem? Okay. All right, so again, our goal is to somehow identify all the heavy hitters in sublinear space. So if there was n elements or something, right? I mean, there's n possible elements coming through the stream. I would just think of them all as integers between 1 and n. Maybe they're bit strings or something. And I wanted somehow, the whole point is I'm not allowed to have a counter for every possible key. So I want to do much less than n counters. I want to do something that's sublinear. So maybe square root n keys would be helpful, right? There's 1,000,000 keys, then you only need to maybe keep counters for 1,000 of them. If it was 1,000,000,000,000, I guess you would need 1,000,000. Is 1,000,000 squared 1,000,000,000? It might be. Okay. But the point is I want to do something much more economic than maintaining a distinct counter for every possible key I see. Okay. All right. So, okay, how is this even possible? Right? How can we possibly keep track of everything without keeping track of everything in some sense? Okay. If I wanted to find, this might be an awkward question to try to answer, but if I wanted to find all the 5% heavy hitters, so all elements that come in at least a 5% frequency of the time, and I wanted to report all their counts, what's sort of like a minimum number of counters I would need? Yeah. Two. Okay, but what if there's 3 heavy hitters? Don't you wish you would have had 3 counters?
But you could kind of figure out the other one.
Okay, so the answer was 2. What? Okay, one was for the total length of the stream, and the other one was
just the one that's like if you're looking for A, then just the amount times A shows.
Okay, and then maybe one for one of the heavy hitters. So the question though is, I want to report all the heavy hitters. So I want more than 2. But how many would I need?
And it is possible for every single number you would need a counter. Just all of them could be heavy hitters.
Yeah, could all the elements be heavy hitters? That would suggest like n counters for n possible keys. Okay, so we're at 2 extremes. On one hand we have 2, on the other hand we have n. I'm looking for something in the middle. Yeah.
Yeah, 20.
20. Why 20?
So if you want 5%, then if all elements appear 5%, then you will have 20.
Okay, so there's only 20. Yes, there are many possible elements, but only 20 of them can occur more than 5% of the time. Right? So there is at least a little bit of hope in the sense that, okay, you have this huge stream and lots of noise and stuff, but you are ultimately interested in a very sparse subset of the data. Right? As some of your output size is small, even though the input size is very big, so there's some hope. Of course, the hard part is you don't know which 20 ahead of time. Okay, but there's some hope. Okay, and there's 2 other reasons we have hope. Okay, besides the fact there's only 25% heavy hitters. One is that we're going to do some randomization, and there's going to be a small chance of failure, but we're going to be able to analyze that chance of failure and kind of control it and really drive it down to 0 rapidly. Okay, but allowing for some error also cuts you some slack. Okay. And the other, we'll see, is that at some level we're going to come up with some approximation criteria. We won't do everything perfectly, maybe if you're really interested in all the 5% heavy hitters, you'll return all the 5% heavy hitters and you'll return maybe a few 4% heavy hitters too. Right? There will be a little bit of error, a little bit of slack. Okay. All right. But that too will analyze and will control, so we'll understand kind of what we're getting. So we'll get a little bit of approximation criteria that cut us a little bit of slack, and we'll also be using hashing and randomization, and we'll accept a very, very small probability of error. Okay, but sometimes when you're in these sort of severe computational settings, you take what you can. Okay, but you take what you can, but we still try to maintain some rigor. Okay. All right, so we're going to introduce two new probabilistic tools. Both you'll get used to quickly, I think. All right, so I'll start with the more mathematical one first. It's called Markov's inequality. Okay, so I think the following fact shouldn't be surprising. If I told you that at most 50% of the population makes twice the average salary of someone in the U.S., right? That should be kind of almost common sense. If I told you, if I told you had a non-negative random variable, and the average was 5, then the most often it can be 10 or bigger is 50%, because average would get too big. Okay, so for example, Markov's inequality for a special case of 2 would say that if you have a non-negative random variable, the probability of that random variable being more than twice the average is at most 50%. Okay? So, I meant to erase. Oh, okay. All right, so the claim is that if you have any non-negative random variable, the odds of it being at least twice the average, no matter what, is at most 1 over 2. So I'll point out that we don't assume too much about x, except for the fact that it's always non-negative. Okay. All right, so of course there's some mathematical notation, but hopefully the proof will almost feel like common sense. So, okay, so if we start with the expected value of x, right, which by definition was, I sum up all the values and the probability of getting that value. Okay. And what we can do is we can restrict the sum to only consider the values that are bigger than twice the average. Okay, so all I'm doing is dropping off some non-negative terms. Okay. And, if I restrict myself to this sum, then I know that all the values are greater than 2 times the expected value of x. Okay, so I sort of pulled this out. And then if I look at the remaining sum, if I look at this remaining sum, this is summing over all the values that are greater than twice the average, summing up their probabilities, which all put together is a probability that our random variable is at least twice the average. Okay. So if I sort of divide the left-hand side by 2 expected value of x, we'll come to this conclusion: I can't exceed twice the average more than half the time. Okay. All right. So 2 was, I just chose 2 for simplicity, you could choose any value bigger than 1 and repeat this proof. You can't be more than 10 times the average, more than 1/10 the time, or else the average would have to be bigger. That's all really the proof is saying. Okay, but this is a very useful style of inequality. So at a high level, the inequality is saying, oh, here's some random variable x. We'll have some random variables in our algorithm. And we'll understand what the expected value of our random variable is. That might be relatively easy. But we want our algorithms to be somewhat robust, and we want to know how often is it going to be close to what we think it should be. Right? So we know, oh, on average it's like this, but now what's the odds that it's way bigger than this? Right? So this will allow us to build a little more robustness into our randomized analysis. Let me make clear an example. Okay, so that was one of our tools. The other tool is we need hash functions. Okay, so I think you guys have seen it in some form before. But the idea is I'm going to take my many keys. Again, our keys are just between 1 and n. Okay, and I'm going to map it to a relatively small set of keys. Okay, so you can think of a big space and a small space, right? And you end up mapping all these things sort of randomly. And we'll look at some explicit constructions in a moment. Okay, but you're hoping that sort of the top level keys get spread out kind of randomly in the bottom level keys. Okay. But what of course can happen if you're mapping a bigger space to a smaller space is you're going to have a lot of collisions. You have to have collisions. Okay, so whenever two keys go to the same one, that's called a collision. Okay? And the general spirit is, for our data might be out of a huge range of possibilities, but only a small subset of the huge range of possibilities. And you're hoping that when these things map down, they will tend to not run into each other too much. Okay, that's a general spirit of most hashing applications. Okay, and then there's now the name of the game is how to be creative about this. So I'll note that hashing is one of the things that work really, really well in real life. Okay, so the most kind of ideal version of a hash function would be to really assign every key a completely random number from the smaller set. Okay, so really I just say, oh, what's the hash for element 1? And I just choose something between 1 and k completely randomly. Then I'd say, oh, what's element 2? And I choose something between 1 and k completely randomly. Okay. And at some level, this is sometimes at least a good model to think about when you're initially designing algorithms because you can assume everything's independent and stuff like that. So it makes your analysis easier. It makes sometimes thinking about it easier. Okay. But when there's no free lunch, okay, to actually write down a function from this distribution, right, it's actually going to require a lot of space. You guys might be able to guess this. So I want to argue that if I was actually going to sort of randomly construct a hash function in its ideal fashion, then I would actually require quite a bit of space. Okay. But how can I try to argue that it needs a lot of space? Lower bounds are always tricky. So how many oh yeah.
Does it have something to do that if you were trying to map, as a one-to-one, you would run into more collisions due to the confined amount of space, like everything would have to land somewhere perfectly. But if you have a lot of space, the number reduces the number of collisions.
No. So collisions become an issue in terms of when we use it. Usually the collisions are bad and something we pay for. But this question is just asking, this is sort of the best possible hash function in the sense that it's the most random. Everything is completely random. But now I'm arguing that, okay, that sounds great, but you'll definitely have to use a lot of space to write down such a function. It's completely random. Okay. So here's the
Yeah, is it something to do with needing a big enough sample from the original distribution in order to use cumulative, God, I just took a stats course, but I don't remember. There's some kind of thing where you can transfer from uniform to other distributions.
That sounds like my stats experience. So intuitively, there's a lot of randomization being used, right? And you need a lot of random bits to generate it, and you can't just like lose that information. But let me. If you look at it differently, you can. It's easier to make this argument. How many possible functions could be produced by this process? So every one of our n elements can have one of k keys, or k values, right? So that's k times k times k times k times k. Yeah. Okay. So there's k to the n possibilities. So if you just try to compress everything in bit strings, but everyone has to have a different bit string, then that gives you a lower bound of log k to the n space, which is n log k. That's basically writing down explicitly the number for every, the hash value for every number. Okay, so there's not much compression going on. Okay, but just the usual log of total number of possibilities is almost the only way I know how to get lower bounds. Okay, so this is ideal, and it's nice to think about when maybe initially designing things, but not super practical because you have to. The whole point is n is really big. Okay. All right, so what we tend to do then is we don't ask for completely random hash functions. We usually ask for hash functions with a limited amount of randomness, and it's going to be enough randomness to suffice for whatever application we're interested in. So I don't know why it's called universal, but it's called universal. A universal hash function is not necessarily evenly spread out and everything like that. It's only just going to focus on, for any two keys, I want sort of the chance of them colliding is 1 over k, which is the size of the space, right? So that would sort of act like an ideal hash function, only in terms of what are the odds of two given keys colliding. Okay, so this is not totally random, or it doesn't require total randomness. Okay, so let me give then a simple example. Okay, so this kind of hash function, which is clearly very limited and very simple, will give you this sort of universal hashing guarantee. Okay, and it's really just ax plus b, where a and b are chosen randomly. You actually have to be a little bit more careful. So you have to choose a prime number p that's bigger. So you choose some prime number b that's bigger than the space you're mapping into. Okay. And so you actually do ax plus b mod p, where p is this prime, and a and b are chosen uniformly at random. A is chosen between 1 and p, and b is chosen between 0 or 1 and p minus 1 and 0 and p minus 1. Okay, you need to do a prime so that it's a field. The integer's modulo prime is a field, so you can do division and stuff. But okay, so this would be in the following, I'm just going to say, oh, we have a universal hash function, but it's really just doing ax plus b, so you only have to write down 2 numbers. Okay, maybe with log n bits to do the arithmetic. Okay, so you only need to write down 2 or 3 numbers to get a universal hash function, as opposed to the n log k space for an ideal hash function. Okay, the only guarantee is that for any 2 particular keys, the odds of them colliding is as if it were completely random, because there's k slots, and we're saying 1 over k. Okay, so this is the general kind of name of the game, is that you have these kind of qualified randomness, and you figure out what you need to get the job done. So next time in hash tables, we'll have a slightly more sophisticated requirement. That's why I'm doing this one first. Okay. Okay, so those are the only 2 kind of probabilistic tools we'll introduce today, and we can go back to the heavy hitters problem. So again, hash functions, Markov's inequality. Okay. All right, so heavy hitters. You have the elements coming one by one, and I want to figure out which ones are the ones that occur a lot. Yeah, I guess I just copied some slides. Okay, so let me fix. Let me set up some notation for our analysis as we start to do some work. So I've decided to just treat the percentage as a variable epsilon. So 5% will be epsilon is equal to 0.05, but it could be 0.01. 1 over a million might be practical because you can hold on to a million counters. And rather than solving the heavy hitter problem directly, identifying all the elements that are in the top 20 or whatever, I'm going to do a slightly more advanced task of trying to estimate the frequency of every element. Okay, so here there's some notion of absolute and relative. So absolute frequency will be the total number of times it comes in. The relative frequency will be the percentage of the element. Okay, so when I'm looking for an epsilon heavy hitter, I'm looking for elements with relative frequency at least epsilon. Okay, and if we can get everyone's relative frequency, then of course then we can look at which ones are big. So we won't do that exactly. Okay, but we're still going to try to estimate the relative frequency of every element. Okay, so I guess I didn't. And the other thing we're going to do is I'm going to estimate the relative frequency up to an epsilon additive error. So actually, realistically, I might have made epsilon equal to half of my heavy hitters threshold. Okay, so I'm given some parameter epsilon, and I want to estimate all of the relative frequencies up to an epsilon additive factor. Okay, so if I chose epsilon to be 0.01, which represents 1%, then I want to be able to, for any query term, say, oh, this comes in this percentage of the time, and be correct up to 1%, plus or minus 1%. Okay. And although we don't have enough space for all the counters, as we've said again and again, the good news is that for most of the elements, 0 is a good estimate, right? So only 1 over epsilon of the elements will have a relative frequency at least epsilon. So almost 100 elements will occur at least 1% of the time. So for the vast majority of queries, 0% would have been a fine answer. Okay, of course, we don't know which ones are zeros and which ones are at least 1%, but that gives us some hope. Okay, so I've shifted the problem a little bit from originally the heavy hitters to slightly more generally trying to estimate the relative frequency of every element up to an epsilon additive factor. Okay. And in general, for the heavy hitters, epsilon additive is not a big deal. Okay, so this is where hashing is going to come into play. So the algorithm itself is actually pretty simple. Okay, so so the general crux of the problem is that I can't allocate a counter for every single element. Okay, so I'm going to allocate a few counters, probably something proportional to 1 over epsilon. So here in this picture, I've allocated 10 over epsilon counters. So if epsilon was 1%, that would be 1,000 counters. Okay. And every time I have an element I come in the stream, right? So I want to increase the counter, the absolute counter, by 1. I'll use my hash function, which will be a universal hash function. It'll map into some slot, and I'll increase that counter by 1. Okay, so each of my limited number of counters actually represents a sum over all the elements that mapped in. Okay, so I'm grouping things up kind of randomly. Does that make sense? So each element comes in, I hash to the appropriate spot, and I increase that counter. Okay. All right, so now, if I wanted to kind of estimate, so using this sort of simple hash set of counters, now I do want to retrieve information, right? And now, so if you ask me, okay, what's the frequency of element I? How would you use this data structure to retrieve the answer, or an estimate of the answer? Yeah.
Could you use the hash function to point to the spot in the
Yeah, you might. It'll hash there, and you would return that counter, right? So we'll just, if you want the frequency of element I, I'll just return the hash counter for element I, okay? Which of course is going to have some errors, right? Because it's taking in all these other, it's also counting up other elements as well, right? So what you return is always going to be an overestimate. There will never be an underestimate of the true frequency of element I, because it may include some counts from other elements. Okay? But why? But does anyone maybe want to try to guess at the intuition and logic? Why? I mean, I'm hoping that I don't overcount by too much. So, what is the hope then? Yeah.
The hope is that you don't have like multiple things that are like really, really popular in the same hash slot.
Yeah, so okay, at some level, exactly. So let's say that M is the total length of the stream. Right? And yeah, especially heavy hitters. But so in general, M is the total length of the stream, so that the whole sum of counters should be M. Okay? And, all of these counts represent, in the extreme case that was suggested, let's say that, I don't know, you have a heavy hitter that's like, represents, half the stream or something, right? And that's okay, so that's out there. Let me do a different color. So you have this big heavy hitter, and you're really hoping that this guy will get hashed somewhere else, right? You've created some extra space. You have 10 times as many counters at some level as strictly necessary. And so you're hoping that the noise will kind of spread out and dodge you. Okay? In fact, we'll do this in a second, but at some level, if the hash function was really an ideal hash function, then the noise should all kind of be spread out uniformly over all the counters. That would be ideal. If everything was kind of small and truly random and stuff, you're hoping that all the other noise is spread out completely uniform at random, which is like epsilon times m over 10 or something. Okay, so there's m total noise. There's m other counts out there. And if you have 10 over epsilon counters, so if you divide it, then sort of the noise would be closer to epsilon m over 10, which is within our tolerance, right? We're looking for epsilon relative frequency and epsilon over 10. Okay, so that's the high-level logic. Okay, is that, okay, there are noise from collisions, from overcounting other things, but you're hoping it's spread out. Okay. And then this is really where it's really great that we allow ourselves some error. I don't think you can do this exactly, right? But if you allow yourself some error, then you have a little bit of wiggle room to do these kinds of things. Okay, so let's do this analysis then. Just to check in. So A is going to refer to the array with 10 over epsilon counters. I guess I'm using W as the width, so to speak. I'll use F sub I to represent the true frequency of an element I. We have a universal hash function. M is the length of the stream. Okay. So, for example, any particular slot of our array of counters, is going to sum up the frequencies of all the elements that map to that spot. Okay. All right, so that's the setup. I think I have it on the right-hand side. Okay, so here then is maybe the key thing, the key analysis for us. So we're going to look at a particular element I. Okay, and that means that this is my estimate, right? A h of I is my estimate for the frequency of element I. Okay, I think as we've already established, this will always be at least as big as the actual frequency of I because it's only throwing in some other counts. Okay, but the claim is that with probability at least 1/2, the error is at most epsilon m over 5. Okay, let me give myself some space. Okay, so the claim is that my overcounting is at most epsilon m over 5, that's within our tolerance of error, with probably at least 1/2. So I have a 1 in 2 chance of getting a good estimate by our definition of good. Okay. All right, so how do we analyze this kind of thing? So maybe the first thing is to say, what do I expect that error to be? What do I expect the magnitude of overcounting to be? That seems to always be a natural first step when we analyze a randomized algorithm. So I might ask, okay, I know I'm going to overestimate, but how much do I overestimate? Okay, so here's the expected value of the total sum minus the true frequency. Okay, we can analyze that first. Our average error, so to speak. Okay, so let me expand out the definition. So this is not random, so we can kind of pull that out. So you have the expected value of. So this value is going to sum over all the elements j with the same hash code as element I, the count of j. Right? And I can pull out minus f sub I because that's actually not random. That's part of the input, that's deterministic, it's separated from the randomness. Okay, so all I've done is kind of expand out what the actual sum would be. Just let me know if when the notation is unclear. Okay. And I can remove from this sum whatever term course. So this is summing over all the elements that collide with element I, but that actually includes element I. So let me you can kind of add and subtract some stuff. So instead I'm just going to sum over all the elements j not equal to I that collides with element I, the frequency of that element. Okay, so might seem notationally heavy, but what it's representing is what is the total kind of sum of frequencies over all collided elements. Okay. All right, now here's where you guys can come in. What's the next step? Yeah. Oh. Okay. Yeah. Okay. So almost automatically, you should think linear of expectation. This will make your life easier. Oh, okay. But we should be careful. So, okay. So there's a little bit of kind of information embedded in this sum. Okay. So if I were to do linear of expectation more carefully, I would really be kind of summing over this quantity. Okay, how would I write this? Okay. I'll put it this way. Xj, where Xj is equal to Fj, if they're equal, and 0. Okay. So what did I do? I invented a random variable xj, which will only count for fj if they collide, otherwise it'll count as 0. Right, so I'm trying to bound the sum of xj's over j's not equal to I. Okay, and that's what I really apply linearity of expectation to. Okay, so I should have. That would have been an intermediate step. Okay. Okay. And now we just have to analyze one of these xj's. It's worth fj if it collides, 0 if not. What would that be? I'm not sure if might need. So because it's a universal hash function, for any other element j, the odds of I and j colliding will be 1 over kind of the small range, which for us was this value w, or 10 over epsilon. So for every other ID, I'll write w for the time being, but w was set to something like 10 over epsilon. It'll be 1 over w times the frequency of j, right? So with probability 1 over w, they do collide and you add in fj, otherwise they don't collide. Okay? And this is, you already see this interaction, universal hash functions were quite limited, but what's going on is because I'm doing an expected analysis, linear of expectation, I don't, because the universal hash functions doesn't say anything about combinations bigger than 2. Right, so it's not really that random, but it's just fine for applications of linearity of expectation because it breaks up into these terms. Okay, so this is at most the total length of the stream divided by w. Okay, which for us was epsilon m over 10. Okay, now the claim though was a little bit different. The claim was that the probability of it exceeding epsilon m over 5 was at most 1/2. So now we know the average noise is epsilon m over 10, but now I'm looking at what are the odds of the noise being at least epsilon m over 5. Okay, so what I'm really interested in is the probability that the amount I overcount by is bigger than epsilon m over 5. Okay, I want to bound this. I want to somehow say that's at most 1/2. Okay. Now, how might I approach this? Yeah.
Use the alpha.
Yeah. Okay. So this Markov's inequality. So this represents twice the average. And I think one thing that's really important that we probably took for granted is that this term is always non-negative because we're only overcounting. So that's subtle but important. Okay. So this is really saying what's the probability that the error is more than twice the average. Okay. So we're saying, okay, the error is always non-negative. What is the probability that the error is more than twice what we expect the error to be? That is at most 1/2. Okay, so we just use some relatively crude, keep in mind that the hash function is just doing ax plus b, so it's not that random. Okay, so we're not taking advantage of any independence or anything like that. We just we assume no independence of collisions. I mean, we assume very little about the collisions, but just enough to get linear of expectation and Markov's inequality. Linear of expectation makes no assumptions on the random variables. Markov's inequality only required the variables to be non-negative. Okay, so this is not looking at a full distribution saying, oh, this is independent, and ripping things apart. It's much more crude. Okay, so that's what it's really saying. It's really saying what are the odds that the estimate is more than, the overestimate is more than twice the expectation, and that's why you get 1/2. Okay, so let me recap. We've done probably the heaviest part of the analysis. So for every element, we've shown that we can get a pretty good estimate with probability at least 1/2. So any particular element, we can do an okay job, right? But now I want to figure out how to get all of the estimates. I want to get all the elements correct with very high probability. Okay, so how do I get all the elements correct with high probability? Any ideas? Yeah.
Run it multiple times.
Run it multiple times. Okay. So, I can think of every time I run this algorithm for a particular element as sort of like a coin toss, right? Every time I run one of these hash counts for a particular element, there's a 1 in 2 chance of being correct, right? So imagine repeatedly flipping coins. What are the odds that the first coin toss is tails, we lose? You guys know this? Yeah. Okay, thank you. And then what are the odds that both of the first 2 coin tosses are?
1/4.
Okay, great. But here comes the hard one. What are the odds that all 100, you get 100 consecutive tails? Yeah. Okay. So the point, though, is that when we do these independent samples, the odds go down, but they go down super fast, right? 1 over 2 to the 100 is a lot of zeros before you get to a non-zero in your decimal. Okay. I mean, what we figured out the number of atoms in the universe is 2 to 260 or something. So you can make 260 copies of this data structure. And now your odds are as small as picking the wrong atom in the universe. Okay, so we're going to make D copies of this sort of hash counters data structures. Okay. And so the total space, just in terms of our variables, will be D times W, keeping in mind that the width of one of these things is W, that's roughly 1 over epsilon. Okay. Okay. So, okay, if I make many copies, but now, okay, so if I want to actually estimate the frequency of a particular element, I have many tables to choose from. Yeah. I'll pick the smallest one. Yeah, okay, so I'll only note that often people suggest picking the average. That's also a reasonable idea, but here, they're all overestimates. So the smallest one will be your most accurate. Okay, so you should pick the minimum overall, I don't know, looking at your kth copy of the data structure, wherever it got hashed in. Okay. All right. I think I wrote something here with that, right? Okay. So again, this will only be a bad estimate if all of your data structures overcounted. Right? So, because you're returning the min, and you're only worried about overcounting. So, if you're only your smallest estimate will be bad only if all the estimates are bad. So that will happen with probability 1 over 2 to the d. Okay. All right. So if we set d, the number of copies, to something like 10 log n. Okay, so not completely independent of n, but log n is okay because you need to write down log n bits to keep track of an ID anyway. And 10 was kind of arbitrary, but then any particular element you're going to mess up on was probability 1 over n to the 10. So make 10 log n copies, and your probability error goes down to 1 over n to the 10. That's minuscule. It goes smaller and smaller. If I wanted to make it n to 11, I would do 11 log n. No big deal, but it goes down by a factor of n. Okay. All right. But now I want to ensure, what we've now shown is that one element is almost definitely going to be done correctly. But I still want to ensure that all the elements will be estimated correctly. So right now I know that the probability of error for one element is basically as small as I want it to be. But now how can I get a guarantee for all elements simultaneously? I want to bound the probability of messing up element 1, or messing up element 2, or messing up element 3, or messing up element 4, or... Okay, so we introduced last class, but actually I realized we might not have used it. I don't remember. Did I miss a slide? Okay, I think I've accidentally deleted a slide. Why do I keep doing this? Okay. Alright, so what we can do is apply the union bound. Okay? So the union bound which was something like, okay, the probability of A happening or B happening is at most the probability of A plus the probability of B. Okay, seems like a simple bound, not a very aggressive bound or tight bound. It doesn't assume independence or anything like that. All these bounds that don't make much assumptions about your events and random variables are just so much more useful when you're making algorithms because things get complicated real quick. Okay. So for us, we kind of want to bound the probability that any element is bad. Okay. Which I might write as sort of the union of all these events. So I might write, I'll write kind of as if it was a sum. I'll take the union over all the elements from 1 to n of the probability that element I is screwed up. Okay. So this is what I want to bound. And the union bound will tell us that I can sum up all the errors independently, or as if they were independent. I shouldn't use independent, maybe that's overloaded. Okay. So here's the key use of the union bound. Okay. So the probability of any element being bad is bounded above by the sum of probabilities of individual elements being bad. So that's a sum of n terms, each of which is at most 1 over n to the 10. Right? We have so much control over the individual error that we can afford to take a union over all of them and just add them all up. Okay. Okay, so then terms times 1 over n to the 10, you get 1 over n to the 9. Okay, so this probability 1 over n to the 9, all of them are correct. All right, so the amount of space we used was roughly log n over epsilon. That's pretty good up to constants, right? Because at some level, to keep track of 1 over epsilon counters, you need 1 over epsilon counters just for the sort of epsilon heavy hitters. And if you're actually going to write down the IDs of the heavy hitters, they would each kind of be log n bits long, right? So in some ways, log n over epsilon is quite good. Okay. Our hidden constant was like 10. And that was to get a 1 over n to the 9 bound. You might have been happy it was 1 over n or 1 over n squared error. Okay. So, when you put everything together, we're able to estimate all of the relative frequencies up to plus or minus epsilon. Okay. Using only log n over epsilon space. Here the log is around n, not epsilon. Okay, so using log n over epsilon space, and with probability of error, polynomially small in n. You increase the constant in that log n over epsilon, and the probability of error just goes down rapidly. You get to control the exponent of your probability of error. So that's a really great trade-off. Okay, and it's amazing, simple idea, but very practical. Okay. So one of the homework problems is, so we didn't actually address the heavy hitters problem, right? At some level, now we're just counting everything, but the elements kind of go through and go past you. So, one approach you can do is you can make 2 passes over the data. In the first pass, you count everything up, and then in the second pass, you go through and anyone with very large frequency you'll hold on to. Okay, but the homework will ask you how to figure out how to do this in 1 pass. Okay. While kind of keeping the space usage comparable. Okay, so you want to kind of find them on the fly as opposed to counting and then finding. All right. Okay, so that's it. So that was this heavy hitters and frequency estimation, and so next time we'll do hash tables, including a pretty sophisticated one. All right, thank you.